Yesterday we discussed these aspects of NMR. So in continuation with this, they just have a revision. What we get number of signals in that NMR spectra, and that tells us about how many different kinds of protons are there in a molecule. Second information we get is the position of these signals, which suggests the electronic environment of each kind of proton. Third is the peak area or integration, which tells us about how many protons of each kind are present in a molecule. And lastly, we look for the splitting of these signals, and that can be correlated with the nearby environment of each proton. So when we look at the PMR spectra of any molecule, usually we'll be looking for these four aspects in the NMR spectra. We have number of signals, and we said it tells us about how many kinds of protons are present in a molecule. So number of signals corresponds to equivalent protons. So the protons which are having same environment around them are termed as equivalent protons, and they give one signal. Whereas non-equivalent protons which are having different environment, they give different signals in the NMR spectra. So here we have discussed example of benzene. All the 6 protons of benzene are equivalent. So we observe only one peak in the NMR spectra of benzene, or particularly say PMR spectra of benzene for all the 6 protons. While if we take example of toluene, then the methyl, 3 protons of methyl and remaining 5 aromatic protons of benzene ring, they are non-equivalent, and we observe 2 signals or 2 peaks in the NMR spectra. So one signal corresponds to 5 aromatic proton of benzene ring, and another signal indicates the 3 proton of methyl group. Next important information we get from the NMR spectra while we study is from the position of signals. The position of signals in the spectrum along the x-axis tells us about the magnetic environment of each set of proton. And this is largely because of the electron density in their environment. Now, this placing of these signals is referred as chemical shift. Okay. So, the position of these signals on the x-axis, when we represent it in the NMR data, it is usually represented with the chemical shift of those protons. It tells us what kind of proton are present in the molecule. A molecule may have aromatic, aliphatic, primary, tertiary, benzylic, vinylic, etc. Different kinds of protons, and they give different signals in the NMR spectra. In the other word, we can say the position of these protons on the PMR spectra is different, and that is a chemical shift. Okay. Now, why we observe this chemical shift is due to the shielding and de-shielding of protons. When we take a circulation of electrons nearby the nuclei, the electron is a charged body and it is circulating, so it generates its magnetic field, and that induced magnetic field can either oppose or reinforce the applied magnetic field. When the induced magnetic field opposes the applied magnetic field, it causes shielding of proton. Whereas when the induced magnetic field reinforces the applied magnetic field, causes de-shielding of proton. Shielding of proton gives upfield absorption, and we observe signals at lower delta values. Whereas de-shielding of proton causes downfield absorption and the signals appear at higher delta values. Now, how to measure these chemical shifts? For that, we need an internal reference or internal standard, and commonly used internal reference is tetramethylsilane, also denoted as TMS. The structure is written here, okay, where silicon is attached to 4-methyl group. Now, why this is used as internal reference? Because of few characteristic properties of this TMS. First and most important, it is inert. It doesn't react with the organic compounds or molecules or the solvents here. Second, all these 12 protons of these tetramethylsilane are equivalent, okay, and they give a strong signal in the PMR. This is a liquid and having low boiling point, 27 degrees Celsius. So we can easily remove it from the sample, and the sample can be recovered back. It is soluble in most of the organic solvents which are used for PMR experiments. It is used as an external reference, okay, when we do the D2O exchange experiments in the PMR spectrum. And most importantly, the electronegativity of silicon here, and most importantly, the silicon being less electronegative. Okay? All these 12 protons, they are highly shielded and they appears at extreme right hand side. The value for these protons is set as 0 or assigned as 0. This is very important. Okay, remember, the value for all these TMS 12 protons or the signal for the TMS is assigned as 0, and then the positions of different peaks are or the difference between these positions is calculated as a chemical shift. Next, how to calculate these chemical shift. Okay? The unit used for representing this chemical shift is delta. Okay? Usually, it is represented with delta. Chemical shifts are expressed in delta, and it's in ppm. So the delta is calculated by the formula observed shift in hertz into 10⁶ divided by operating frequency in megahertz. For example, if we take a PMR of a 60 megahertz instrument, then the chemical shift, okay, is calculated delta equal to observed shift into 10⁶ divided by 60 megahertz instrument, so 60 into 10⁶. It is important to note that the delta value or the chemical shift value is independent of operating frequency. For example, if I take NMR or peak for TMS in 60 megahertz and 100 megahertz instrument, okay, and using above formula to calculate the delta value, we can see the value will appear to be 1. So here it is understand that delta is independent of operating frequency of that instrument. Next. Now, the correlation between chemical shift and chemical equivalence. It has been found that protons in a molecule that are chemically identical environment will often show the same chemical shift. they appears at a one signal. So protons with the same chemical shift are chemically equivalent, and this chemical equivalence can be evaluated through symmetry. Whereas protons in the different chemical environments have different chemical shift. So if the protons are in a different chemical environment, they shows different chemical shift. So a signal is produced for each kind of a proton. These are the few representative values, shift values, okay, of commonly occurring protons. So between 1 to 2 we'll be having aliphatic, primary, secondary, tertiary. Then we have olefinic, uh, uh, vinylic, allylic, okay, olefinic between 5 to 6, aromatic between 7, 6 to 8, aldehydic between 9.5, and then we have acidic in the range of 10 to 11. So these are the few chemical shift ranges for commonly occurring protons. The table here also gives the range of chemical shifts, okay, which are represented in delta ppm, okay, and one can easily guess which kind of proton is present, okay, in the molecule by looking at these chemical shifts. These are the few sample PMR spectra. Here we can see benzene, all the 6 aromatic protons gives only one signal. They are chemically equivalent and it gives only one signal. The chemical shift value delta is near about 7.5 ppm. While when we have cyclohexane, these are aliphatic and the protons are shielded and they appear around 1.4, delta equal to 1.4 ppm. Another example is of acetic acid. Here, in the acetic acid, we get two signals. One is for the 3-methyl protons, okay, which are attached to this carbonyl group, and the signal is slightly downfield as compared to aliphatic methyl groups, and it is around 2.1 to 2.2 delta. Whereas this acidic proton gives a signal around 11 delta value. Next important information we get from the NMR is about peak area or integration of signals. The area under the signal tells us about how many protons are there in each set. That is, the area under each signal in a PMR spectrum proportional to the number of hydrogen atoms producing that signal. It can be understood by this representative PMR spectra of paraxylene. Okay. Here we can see two signals in the NMR spectra. There are two different sets of protons. 6 protons of 2 methyl groups gives one signal, and 4 aromatic protons of benzene ring give another signal around 7 delta. The 6 methyl uh, 6 protons of 2 methyl groups give signal at 2.2, that is corresponding to the 6 protons. And the integration here or the peak height gives us idea about there are 4 protons, okay? The height is approximately 1, and for the 6 proton the height is 1.5. So if we calculate the peak area, or by integrating this, we'll be arriving at a number that we have 4 aromatic protons and we have 6 protons which are benzylic in nature.